So hi everyone, I'm Djoume and I'm going to talk about Android from the bottom up. Just one slide about me. I'm a lead developer at Shopify. I'm also the organizer of a team lead Toronto Meetup, another great meetup that I encourage all of you to check out. And for the past 10 years, I've been focusing on back-end web application development, meaning I haven't done any Android. And it's only this year that I decided to do some Android development and try to learn how to build my first Android app. And to be honest with you, I didn't think this was going to be a big challenge because I knew Java, I'd done desktop GUI application development before, so how hard could that be? I just look at the documentation, and then I would come across those things and just be scared away, what's going on? Pretty scary stuff. So actually, be reminded of the time where I was learning Git. How many of you guys are using Git? Probably, yeah, everyone. How many of you guys understand Git? All right. So I remember when I started using Git, I was like, oh, how hard could that be? I know Subversion, right? So must be the same. Severely mistaken. And it's only when I read that article, Git from the bottom up, that I started, everything started to make sense. So this is my goal for today, is to try to make sense of Android, why Android is so different from desktop application. It's kind of the opposite talk of Dario, who came from the top down. I'm going to try bottom up. So let's start with the very beginning. What are the design constraints of a system? That have shaped the Android OS and application framework. So we know it's a large-scale consumer device. But it needs to run third-party code, so security is going to be key. We also know that in order to compete, we need to be able to provide a compelling user experience, rich graphic, responsiveness, all of this within an embedded environment, which means limited memory, slow CPU, and limited battery life. Okay, I want to start with those constraints and see how we can get to the application framework. So what are potential solutions to those problems? So we have a memory issue. Oh, I know what to do. How about we just use thread, right, and share memory between different applications? So that says memory, but that's the worst idea in terms of security, especially if you think of third-party code. Now, third-party application can access first-party memory. It's just going to be a nightmare. So terrible idea. So we have to keep those processes separate. So all we have to do, because we don't have enough memory for all of those processes, is to kill the processes that we no longer need. And this way we can minimize the memory use. Except that this is terrible for UX, especially with a slow CPU. If every time I switch app, I have to restart the entire application, it's going to be a very bad user experience. Next idea is just to pause those processes. This way we can start them back quickly. So it's good for CPU. But we are kind of back to square one. If we pause them and keep them in memory, now we don't have enough memory to keep those processes along. So what do we do? How about we do all of them and see what happens? So let's start with the first constraint, security, and talk about how Android addresses it. So with Android, each app runs under its own separate process, but also separate Unix user, which is different from traditional desktop application. If you, on your Linux desktop or on your Mac desktop, typically all the apps run under the logged-in user. On Android, each app runs under a different Unix user. That's Android way of leveraging Unix security model and to provide, to prevent one application from accessing the resource of another application, beyond memory, even the CPU, the file, the network, all of that can be compartmentalized for each application. The other thing that Android does is it gives very limited permission to those application Unix users. They don't have any access to hardware in particular, and if they need to access the hardware, let's say find the location of a user, or access the camera or anything like that, they have to talk through another service that is going to be able to enforce much more granular permission. I think I just went through all of this, yes. So there's this concept of system service, which we'll get back to in a moment. But before we do that, I have to talk about So if we follow this approach for security, there's the obvious memory issue that I alluded to earlier. And that's where I'm going to introduce Zygote. So Zygote is Android's way of sharing memory safely between processes. And the way it works is Zygote is a daemon that is started very early on at boot. And the main function of Zygote looks like this. Like I just remove a little bit of tracing from the code. So it's pretty simple. It does a bunch of preloading. Then it does a bunch of garbage collection. And then start the system server, which we're going to get back to in a moment. And then there's a loop that waits for connection to start new application. So it listens on that socket and wait for request to start new application. If any of you have done any backend web application development like me, I immediately recognize that pattern. That's the way we minimize memory usage on web server. So we preload as much as possible, and then we fork. And that saves memory because Linux, by default, use a copy on write mechanism. So when we fork, we actually don't copy any of the memory from one process to another up until the child process tries to write to a memory. But because all of these are read-only pages, like we're talking about the Java system class and resources, they are never going to be copied over, meaning we can share a lot more memory. Let me show you this through a diagram. So think of this box as the memory space of the init process. Init is the first process that is run on any Unix system. So in its memory space, there is a little bit of space that is for the kernel. That's how the init process is able to make system call and talk to the network, things like that. And there is like native libraries. So those are like the memory pages for the C library or other native library that init needs to do its job. So init's role is to start the rest of the system. So the first thing init's going to do is to start a bunch of daemon processes. I'm not going to talk much about those, but like between those two processes, the native library are not copied over. They only use one. They're only copied once in the physical memory. And then init is going to start the Zygote. As I mentioned, the Zygote is going to preload a bunch of stuff. So that includes the Dalvik VM and all the system classes and resource. And then Zygote itself is going to fork to create the system server process as well as the application processes. And what's important to note here is that all the green stuff, there is only one copy in physical memory, and the yellow stuff, there is only one copy in physical memory. That means that the memory effectively used by the system server is only the blue stuff, like the additional memory for system server specific code or resource. Same for the application. So that reduces considerably memory usage without compromising the security model. So let's do a quick check-in. So Zygote is good in terms of security because we still have a process isolation. Actually, we have even more than that. We preserve the Unix user isolation as well. Zygote is good for memory because of that copy on write mechanism I just mentioned. Another thing to note is, we'll see it later actually. There is also like multiple thread being used by the system server to save additional memory. And in terms of being within an embedded environment with a slow CPU, Zygote is good because we preload a whole bunch of stuff, but we don't have to do every time we start a new app. So that saves time. Let's do a quick demo of that. So where is my cursor? So I just started a phone on the left, and I'm going to shell into it using the IDB shell command. So now I'm on the phone. I just want to show you the list of processes that are running. Actually, let me just leave this. So I'm not going to go through every single one of them. Don't worry. Just want to show you the most important one. So, and to prove that I wasn't just talking nonsense. So the first process here is init. You see its PID is 1. This is its parent PID. So it's 0 because the kernel created init. So I just want you to keep note of that one here. Then there's a whole bunch of kernel thread that I'm just going to ignore for the purpose of this presentation. If I scroll down, I'm going to find some interesting processes. So one of them is going to be Zygote here. So as I mentioned, the parent process of Zygote is 1, which means init started it. And 1384 here is Zygote process ID. And this is interesting because if you just look down, there's a thing called the system server, whose parent process is 1384, meaning it was created by Zygote. And if you look at the rest of the system, there's a bunch of apps that are actually running, and they are all created by Zygote. They all have the same parent process, and they are all sharing all the memory that I just showed you. What else is there? Oh, and another thing I wanted to mention is if I look at the system server process, I already lost it. So I got system server. So its PID is 1653. If I look at the thread of that system server, we're going to see that there are many. And that's where we found most of the system services to access the hardware. So Activity Manager, we will get back to this one, but there's probably others that you guys are going to recognize. Sensor service, camera service, alarm manager. So the system server has access to the hardware and is going to provide this service to the other application. If we go back to like all those processes, we see that those apps, they run under those weird username, U0A16, and like it's different username for every single app, while the system server run under the system user. This is a privileged user that has special permission to access the hardware. Cool. So now that we have done this, just need to find my cursor again. Oh, here. And go back. So I just said that those application needs to talk to the system server in order to access the hardware. Let's say the vibration service to make the device vibrate. But they are running under different processes. So how do they do that? How does one application talk to the system server to trigger a vibration on the device? So that's a problem that Android needs to solve. And that's a problem that Android has a special way of solving, which is using something called the binder. So binder is another, it's Android's mechanism to handle inter-process communication or remote procedure call. It's actually not native from Android. It comes from BOS, but today's primary use case is Android. And it's implemented as a kernel driver and a set of user space library. So application can talk to each other, processes can talk to each other through the binder by making a system call to the binder device file, like /dev/binder, using the IO control system call. And the way it works is you pass in an integer or a long to identify the service you want to talk to, another integer to identify the method on that service that you want to call, and you pass in a buffer that has like the parameter of the method that you want to call, as well as some space for the return value. So let's look with a diagram of how this works. So the system server on the left, the app on the right, and like the kernel driver. I don't know if you remember earlier, I showed like the memory space of those processes, and the kernel was shared across all those processes. So that's where binder lives, and that's what enables that cross-process communication. So the way it works is when the vibrator service starts, it's going to start polling on that device driver. It's not actually the poll system call, but it's effectively the same thing. And when a client, my app in that case, wants to get the device to vibrate, it's going to do that IO control system call and send the parameter. I want to talk to the vibrator service, call the method vibrate with the parameter 500 milliseconds, and the binder is going to propagate that request to the system server. One interesting thing that the binder is going to do is going to add to the request information about the caller, so which process ID and which user ID is making that request, which will enable the receiving service to make additional permission check. But before we get into that, actually, there's one more problem we have to solve here is like, how do I know, like, how to talk to the vibrator service? Like, what's this? I mentioned an integer earlier to identify it. Like, how do I find that out? So there's an additional service here that is important, whose name is the service manager. So that's like the yellow page for all those services. At the beginning of the system, the service manager is going to register itself as what Binder call the context manager, meaning I'm going to be the directory for all the services. If someone needs to talk to a service, just ask me and I will give you the address. And then service manager is going to poll the Binder device driver for requests for service resolution. Whenever a service starts, it's going to register itself with the service manager. Binder knows where the service manager is because it's the first service that it's bound to. So it's going to tell service manager, this PID is the vibrator service. And then the vibrator service starts waiting for requests. When my client, my app wants to make the device vibrate, it can ask Binder, where is the vibrator service? Binder proxy that request to the service manager, who respond back to the client. Now the client has a handle to the vibrator service and can send the request to get the device to vibrate. Hopefully that makes sense. And I have another demo here. Yes, let me show you a couple of things to make this more concrete. So if I redo my PS, we're going to find that very early on, there is service manager here being started. That's the guy I'm talking about that is going to like know about all the other services. And actually, you can query the service manager from the command line using the command service list. And this is going to request through Binder the service manager to give us a list of all the services that are running on the system. And there is, on this system, 100 services running. If I scroll up. Yes. And so those services include the carrier config service, the phone service, the, the media service, all of those things. And this also indicates like the interface that those services implement, so that tells me which method I can call on those services. You can even call a service using the command line. So I can do service call, let's call the phone service. Now I have to pass in the parameter. So actually first a method. So I'm going to call the first method on the phone service. So I put 1. And then the parameter, I have to put S16 to indicate that the parameter is going to be a string. And then I can call, let's say I'm going to call Eric. 1, 2, 3, 7. And that trigger the dialer to pop up on the screen. So what happened here is like from the command line, I send a request to the phone service to that trigger opening the dialer application. This is not actually Eric's phone number, right? Or is it? Maybe it is. All right. So now let's go higher level. This is what it looks like at the Java level, right? So you can use the get system service method to get access to a service. So line 3 here is a call to the service manager to get that handle or that proxy, so you can call a method on that service. Like you couldn't tell here that this is talking to another process. And line 5 is again making a call to the vibrator service under the hood. So that V variable is a proxy to that remote process. So line 5 is a remote procedure call. So that's nice, but very often you want to do more than just making requests. You also be notified of when things happen. So an example would be like the sensor service if you want to be notified when like the device is shaken. So the way you can implement this is by adding having another thread on the client that is going to act as a service. So the app is also going to act as a service, and this other thread is going to listen for callback. So the client, instead of just asking the sensor to do something, is going to start polling like on that additional thread, and it can ask a binder to get the sensor service and then to register itself as a listener. So that request is going to be propagated to the sensor service, and at a later time when something happened that is worth communicating, the sensor service can call back to the client. So the client is also acting as a service. So that gives us that two-way communication. Right, and this is the higher level version of it that is exposed through the application framework. So now instead of getting a simple proxy, you get a manager, like that sensor manager line 2. The difference here is that with a manager, you can register listener. And so on line 8, we register this activity as a listener for that service. So line 8 here is again a remote procedure call, like this is making a request to the sensor service to register this activity as a listener. And the line 11, the on sensor change, is going to be called back from this other process that is the system manager where the sensor service is living. Hopefully that makes sense. And that code is executed on a separate thread. So now let's do a quick talk about binder and security. So binder has a couple of special features that's going to make it a really good candidate for Android. So a few things that binder does. One is it only allows registration from trusted UIDs. So only the radio UID can register as a phone service, for instance. This, by the way, is hard-coded into the binder source code, unlike what is the ID of a phone service, which is dynamic, and you have to query it at runtime. This list of trusted UID are hard-coded into the OSP. Also, when receiving a remote method call, as I indicated earlier, binder is going to add information such as the PID and the UID of the caller so that the receiver, the service, can do additional security checking. So what typically the service will do is call another service, the package service, to convert the UID into an application. Remember that every app runs as a separate user, so therefore if you got a user, you can get the app, and from the app you can get the permission that this app has, and from those permissions you can decide whether or not to accept that vibrate method call, for instance. Does this make sense? Now let's talk about performance. So binder has two really cool features that makes it really good in terms of performance. So the traditional way you will do inter-process communication on Unix is either via socket, like Zygote does, or via pipe. But with socket and pipe, you have to copy the data twice. You have to copy it from the sender process into the kernel space and then back into the receiving process space. Instead, with binder, each process does a mmap of the binder shared memory space into its own process address space, which means that when you make a RPC with binder, let's say you talk to the sensor service and you are sending those parameters, they only need to be copied once from the sender process into the kernel space. So that single data copy makes it really performant, and it means that in practice, most of the time, like the same CPU time slice can be used to go from the calling process to the receiving process and back into the caller thread. So it's highly performant, and it's excellent for latency, for instance. The other special trick that binder has, it has the ability to share a file descriptor between processes. So let's say you want to play some MP3, so you can't do that directly because you don't have access to the hardware. So you need to talk to the media service. Now, if you have to stream all of the audio data through binder, it's not going to be very performant. It's not going to be good also for memory. Instead, what binder allows you to do is to just send the file descriptor of the MP3 file to the media service, and the media service is going to take care of playing that file for you. So it's just a single integer that you have to pass around. And by the way, this is also used for graphics composition. So that's how Surface Flinger is going to share those frame buffer with application. So let's do a quick check. Security, we've got those fine-grained permission, check. Low memory, one data copy, check. And slow CPU, there's almost no scheduling, so it's very good for slow CPU. Check, check, check. Now we have to talk about the activity manager. So earlier I said we're going to keep those processes around because otherwise it's going to be not responsive. But we might have a time to like terminate some of them or at least pause some of them. The issue is like, how do we do that? On a traditional Unix system, it's very hard to do. And Activity Manager is the service in charge of making that possible. So let's look at how we start an application. So we click on the launcher application. That launcher application is going to talk to the Activity Manager. It's a service as well, living on the system server, as I showed you earlier. So through Binder, the launcher application can make the request to the Activity Manager to start this other activity or this other application. The Activity Manager is the one actually talking to Zygote through that socket to say start, like fork and start a new process for this application. Zygote is going to make sure that new process is being created and is going to initialize the application. And now we've got those three processes, and somehow Activity Manager needs to figure out, okay, how do I pause the launcher and resume the application. So in traditional Unix system, what we have is one entry point, like this main function, and maybe you have a loop in there. And if that's the way it is implemented, Activity Manager has no way to pause the application, at the right time or resume it. So what Android did, it broke that main function into separate app component. Unlike architecture component, those are app component, and their purpose is not to organize the inside of your app, which is what I thought when I first came to Android, but their single purpose is to make it possible for the system to manage memory, CPU, battery life, and those things. So to expose more about what your app is doing to the system so that the system can properly manage the resource of the. So you already know those components. So main is broken down into several callbacks to give control to the system over starting, stopping, pausing apps. And those components are activities. No, I need to explain what they are, probably not. Broadcast receiver. So I would maybe say a word about broadcast receiver. So this component gives the ability to the system to only run your code when it's needed. So for instance, on boot or on a schedule, meaning that the system has the ability to maybe keep your app process running or terminate it however it wants while fulfilling the need here. And the other kind that is relevant here are services. There's actually three kinds. So like things like music playback. So that tells the system, I have something running in the background and the user is highly aware of it. So if you're killing me, the user is going to notice and probably not going to like it. But I have this other thing, background download. The user is not really aware of it. So you can kill this as long as you can resume it at a later time. That's totally fine. And there's a third kind, like bound services. So you are saying like this background service is actually an API for some other activity. Therefore, it depends on that activity. If its activity is resumed, like you should not kill my service because the user is going to notice. But if its activity is paused, you can dispose of the memory used by my process. The fourth kind are content provider. They're not really relevant for this talk. I just list them for the sake of completeness. So now one more level of abstraction that Android adds, which are intent. So intent are actually abstraction over those binder RPC messages. And it looks like this. You can create an intent by instantiating the class, adding some data, and then call the start service method on it. So this is going to make like a binder call behind the scene to start up that process if it needs to be started or resume it and schedule the code to be executed. There's another kind of intent that are very interesting, which are implicit intent. We don't have to know at compile time which app is or which class needs to be loaded in memory. We can just record some detail about the type of action that we want to do. So we just want to share some text. And at the time of execution, the activity manager can figure out, okay, which app is best suited to fulfill that request and start that process instead. So all of that flexibility comes from the fact that we rely on binder under the hood. So this is, I think this is my last slide, yeah. So that's how all of this works. So at the high level, it looks like some callbacks that are magically called whenever is a good time, and those intent that are like some very abstract concept. And now you can hopefully see that under the hood, it's just some inter-process communication, or for the purpose of minimizing like battery use, memory use, and maximizing responsiveness of the system. That's all I've got. I'll welcome any question you might have. Question? Yes? Right, the pole star, you mean?
I was wondering, like, are these systems like actually looping and kind of like checking in periodically to see something's available, or are there
right. Where is this? So there is an I/O control. Actually, it's not a. Let's try if I can find my slide. This guy, right?
Yeah.
Or like I think I have it here. So this pole star is actually another I/O control that is going to be blocking. So the process is going to be blocked until there is a request, and then when the request comes in, the kernel is going to reschedule that process. So we are not like looping over the file. It's much more efficient. That's why I call it pole. It effectively acts as a pole, like system call. Yeah. So which one? Like
Sorry, the very last one.
all right, getting there. Animation, eh?
I guess that's happening. It's forking a new process every time you start a new activity within your app. So that's not.
Sorry, this one? Not so. Activity manager knows which process are currently running because its job is to like start and stop those processes. So if like one app can have multiple activities and services hosted within that same process. So if the app is not already running, activity manager is going to start up that process and then proxy the request. If the process is already running, it can just proxy that request, and it's going to like call either like on resume, on start, and all of that on that remote thread. Yes?
So for the permissions, what part is managing the permissions, the sandbox, to make sure like apps aren't accessing things, they don't have permissions?
So there's like the Unix things that I mentioned. So like by default, one Unix user doesn't have access to another Unix user resource, such as like files. So if your app is creating a file, it's going to be visible to that app only because it's a different user than the other app. And then at the service level, so let's say, like when you install an app, this app wants access to your location, like that kind of permission. All of this is going to be recorded by the package manager, which is another service. And all the other services are supposed to check with the package manager service to see if the requesting app has the right permission. So whenever an app receives a request, it converts the user ID to the app. And then from the app, it can get the list of permission, and from that list of permission, it can check if like is there like vibration in there. Yes, let the request go through, not through an exception. That make sense? Yes, go ahead.
Are there any kind of, I mean, like I know there are, but like if you could kind of summarize the differences in what happens when you launch like a service under a different PID?
Under a different process,
Yeah.
you mean? What do you mean? What happened?
It's like, you know, you can launch a service under a different process.
Yes.
In your whole like overview, is there any differences like where that would kind of in how the system would maintain that and communicate with like that kind of thing?
I can make two comments maybe related to that. So one is sometimes within an app you call like your own service that might be like living under the same process or like another activity. So when you do that, actually it doesn't go through the activity manager, just go through binder and back to the application. If you have two processes, that communication is going to go through a binder. So let me go back to that slide here, this one. So as you see here, there's like two threads on that client process. So if your service is like another process, it's going to have also like another, actually that second thread that says pool, this is actually a thread pool. And if you have two, and this is a set of thread pool to handle this binder request. So at a higher level in the application framework, this is exposed as a looper. So if I have two processes, and let's say the first one is making a request to the second one, is going to go through binder, like being serialized to a binder message, sent to the other process, going to be picked up by its binder thread pool, and executed on the other process, and the result is going to go back through a binder as well. Pretty much everything goes through binder with Android. Like the only exception is like Zygote listen to that socket. Yes. Yeah. Yeah. Go ahead.
You mentioned the Git from the bottom up. Is there a similar input that goes to this?
There's a couple of like Android internals is a book that has where some of this come from, but it's like very short. Like there's like 3 pages on it, and like the book is like 300 pages. And there's embedded development with Android that has also a little bit of that. But typically those books focuses on like the AOSP and how to build your custom images. I haven't found like I pieced together a whole bunch of different talk and and look at the source code to like make sense of what was going on here. So maybe, I don't know, it's a good opportunity to write a book if anyone is interested. I won't do it. That's it? Okay. Thank you very much.